So thank you very much for giving me this opportunity to share my research. Let us start with my talk. So the title of my talk is Tensor Computations with Image Applications. So specifically in this talk, is it audible properly?
Sorry.
Is it audible properly?
Yeah.
Yes. So in this talk, so we'll talk about, first of all, introduction and motivation of these tensors, and then different computations, like a different way how to compute these tensors. First of all, T product, and then we'll talk about M product. So then we'll talk about a specific image application where we can apply our tensors. So before that, let us start what is tensor. So tensor is a type of data structure that is used in machine learning to represent various kinds of object. That object include scalar, vector, array, and matrices, along with others also. Like you think about, this is a box. So inside that box, you can put it scalars, vector, array, matrices, and itself tensor also. Many people say in many way what is tensor. So we can say that a tensor is a multi-dimensional arrays or higher dimensional generalization of matrix or vectors. So here, if you think about that matrix and vectors, then there is some directions. So that directions represent order of the tensor. So the formal definition say that the order of a tensor is defined by the number of directions required to describe it. For example, let's say scalar. Scalar is a quantity that there is no directions. However, if you see the vector, then vector comes like either it's a row vector or column vectors. So both in one direction. So this is row wise and this is column wise. And then comes to the matrix. So matrix is a second order tensor. That means that is two direction. One is row wise, one is column wise. And then third order tensor, that is cubic, like a cube structure. And that is one is a row and one is column and one is vertical directions. That is a third order tensor. Then come to the fourth order tensor. So the fourth order tensor is basically that is a column vector, and column vector, that each column is a cube. So as a column vector, that is one directions, and each vector, or sorry, each object, that object is a 3D or like cube. So cube, here one more, so that fourth order tensor. And then suppose you have a matrix. So instead of matrix elements, we can put it like a cube. Each element is a cube. So cube means a third order tensor, and a matrix is a like row and column. So these are two. So fifth order tensor. So similarly, we can say that a cube and each elements of a cube is itself cube. So that means this is a sixth order tensor. So now I hope you get the fair idea of what is tensor. Now come to this point. So how we represent this tensor? So you know that in matrix, we can say that there is a row and a column. But if it is in a third order tensor, we have to give some name, how to represent, how to say that this direction or this direction, something like this. So the higher order analog, matrix rows and columns, we called fibers. That means mode 1 fiber, mode 2 fiber, mode 3 fibers. In this way, we can call. For a particular example, if you see that third order tensor. So third order tensor, as I told you, like a matrix is a second order tensor. So that means column and row. So similarly, some extent we can say third order tensor. One is column, one is row, and one is tube. And as I told you that we can call different fibers like mode 1 fiber, mode 2 fiber, and so on. So here we can say that column fibers, row fibers, and tube fibers. For example, if you see, so this is a mode 1 fiber, and mode 2 means this is, and mode 3, this third. So column, row, and a tube. And then slices. Other way we can represent tensor. So that way is slices, like a bread. We can cut it horizontally, vertically, and frontally. So in generally, the breads are cut in such a way, frontal slices. So different way we can make it. Now, so the application point of view. So as we are specifically focused for image applications, however, there are many applications in tensors. For example, like multilinear algebra. So one simple example, multilinear algebra, that AX equal to B, that linear system of equation, we are trying to solve it, and many applications that have, like AX equal to B. So in similar extent or same way, we can see that A is a tensor, X is a tensor, and B is a tensor. This is a multilinear system. And that multilinear systems has also many applications. In this talk, we'll talk about one specific applications in this multilinear algebra. Apart from that, neurosciences, hypergraph, and software libraries and programming language also use tensors, like tensor processing unit. So usually that CPU, now TPU they are using. And statistics, big data analysis, geophysics. There are many applications in geophysics. Suppose we are sitting in different location. Let's say someone sitting in India, someone sitting in USA, someone sitting in some place in Europe, and some places in Russia. That means 4 different places we are standing. How to get the data in different places? Suppose in India, we have different time zone, we have different temperature, different rainfall, different latitude, different longitude. So there are 5 different information we like to collect it. By the same way, let's say we are collecting different places like in USA, different time zone, different latitude, different longitude, 3 information. Then temperature, 4th information, rainfall, 5th information. So five information we are collecting, and different places means for a particular example, 4 different places and 5 information. How to store that all information? So you can say that I can write in India, temperature, pressure, something like these 5 different columns. Then like in USA, Europe, and Russia, some places we can write it. But whenever we need some operations based on temperature wise, based on pressure wise, based on rainfall wise, time zone wise, it is difficult to handle. I cannot say that this is impossible. This is possible, but it is difficult. So to avoid these difficulties, we need tensor structure. That means like in a matrix A of ij, I is one direction, j is one direction. So here we need as 5th different information we need. So we can say that a 5th order tensor is required. A of I1, I2, I3, I4, I5. I1 is, let's say, temperature, I2 is pressure, and like this. So when we call it like something like temperature wise, pressure wise, it is easy to visualize, easy to analysis, easy to process. So this is the tensor applications. So as I told you, like particular, we can focus on image applications. Let us consider one image. So this is a simple colorful image or color image. So as you know that this color image has some intensity. One pixel has some intensity in the sense red, green, and blue, RGB. Based on RGB, you can generate millions of color. So that means one pixel represent only three RGB, red, green, and blue. That means in we can make it a tensor representation. That one is red matrix, green matrix, and blue matrix. Based on this RGB, that means a third order tensor, we can do whatever that operations, whatever that processing, we can do it, image processing. Now come to the color video. So let us you consider like in a video how we can represent in tensor format. So as I told you, like a color image is a third order tensor. So video is a collection of frames. Let's say you can connect 20 frames or 30 frames or 100 frames. So collection of 100 frames, we can make it a tensor. Hello. Yeah. So collection of frames. So these frames, so let's say 10 frames, we can make it a fourth order video. Okay. Now some relationship data. So relational data is a collection of relations among multiple objects. For example, let's say some user is there. You can say that for user particular in this screen, and then some items. So items, let's say spec and light, hat, and umbrella. So one user required one item. So this representation, we can make it easily as a matrix representation. However, if you add one more things, like, time, this particular user required this time, these items. So this is difficult to handle in matrix representation. Whereas tensor representation, we can make it. So this is a third order tensor. So relationship of a three tuple is a third order tensor. Relationship pair, like, two user and items, we can say that matrix is a second order array. That is second order matrix. And let's say if you increase that way, so we can say that tensor representation is generally higher dimensional as and large scale. For example, let's say 1,000 users, 1,000 items, and 1,000 times. So we can make it 10 to the power 9 relationship. So tensor is basically develop tensor model or tensor based applications. We need efficiency, scalability, and product reliability. You understand? So like efficiency, scalability, productivity, and reliability. So all these things is required tensor representation. Now, how to do it? The computation. So computation point of view. So let's say, okay. So suppose A is a matrix and B is a matrix. Then C is a product of is it audible properly?
We did not hear you.
Yeah, is it okay?
Now it's okay.
Okay. Suppose A is a tensor, sorry, A is a matrix and B is a matrix. So the product C is a multiplication of A and B. And it is easy to find it. Then there is one specific way that multiplication C of Ij equal to A of Ik, B of Kj. And if you extend that one, like order of the tensor, so that tensor is second order tensor. So if A is like I1, I2, IP, P is greater than 2. 2 is why greater than 2? So 2 is simple like a matrix. So that's why we need third order tensor or fourth order or simple like P is greater than 2. So here P, if you consider, hello? Yeah.
We hear you, no problem.
Okay. So P is even. P is even, that means even order tensor. P is odd, that is odd order tensor. So in specific, let's say A is a third order tensor. So third order tensor, how we multiply? Addition is okay. We can say that addition of two tensor. But when you talk about the multiplication, call to simple the inverse, it is difficult. So in theory and computations, we need tensor multiplication, tensor inverse, and tensor decomposition. So what is decomposition? Again, decomposition is like making a factor, like a number. Suppose you can say 36. So you can say 2 into 18 or 6 into 6. And matrix factorization, like a matrix, so we can make it LU decomposition or LU factorization, singular value decomposition, and eigenvalue decomposition, QR decomposition. There are many decomposition is there. Why not we extend the same idea in tensor format? So tensor decomposition is basically that is useful in similar line, like in a matrix factorization. And then image deblurring or image compression. What is image deblurring? Suppose you are standing in a place and some accident happen, and that vehicle is basically run away with accident and run away. So we have to detect that number plate, that car number plate or that vehicle number plate. So it is difficult, let's say, to get that number plate number. So whatever that raw image is available, so we have to make it in proper so that we can get clear visible of number plate. So how to make it in blur free that image or blur free number plate? So how we use the tensor for this? And then face recognition. Suppose you are going a place where security is there. So each person, it is very difficult to stay one place and make a detection and then say go out or go in or go out. However, we can quickly how we can do the face recognition. Someone is already moving, then computer can get it. Like toll road. So that vehicle sticker automatically detect quickly. And then higher dimensional partial differential equations. So you can say that all these things is happen before the tensor computations. So what is the new? So the common framework for the tensor computation is like a traditional way. What people do, so they turn the tensor into a matrix, and through matrix computations discover things about the about the matrix. And now you have matrix information, all these things. Draw conclusion about the tensor based what you learn from the matrix. So think about like your left hand is a tensor and right hand is a matrix. But you need left hand side or tensor information. They're making a map like in tensor to matrix, and the right hand side is your matrix. So that matrix information, whatever that they are gathering, they draw the conclusion and send back like in a inverse way and get this information. So this way, like required more computational resources because tensor to matrix and draw conclusion and then go back to tensor. So some after that some progress of the tensor happen. One is N mode product, that is 2000, and then T product 2011, and SAO product and then C product and M product. These things happen, and some references also there based on this product. So we'll talk about specifically in the latest available tensor product, that C product and M product. So what is, let's come to the like a traditional tensor product like Einstein product. Even if till now the Google and other, they are using the Einstein product. They are not come to the T product and M products way. So some people or some researcher, they search is tensor product. So they are, the Google is giving their different way. That's no fixed way. They are talking about all Einstein product way. Some people say that okay, T product way, M product way. So this is lot of confusion is also there. So the confusion clarity, now I'm giving you Einstein product, T product, and some extent M product with applications. In the like short time of the span, let us talk about the first of all Einstein product. So Einstein product is simple like A is a matrix. That matrix is size this, B is a matrix of size this. So multiplication is this. So Einstein product is simple adding the 1-1 loop. For example, now I am not going to the definitions, mathematical definition. Let us come to the example. Then we will go to the definition. A is a 3, A is a fourth order tensor, 3, 4, 5, 6. And V is a tensor, that size is 5, 6, 7, 8. The multiplication of a two tensor, A and B, is A star 2. Then people say that what is star 2? Star 2 is basically because two index we are overlapping. So that's why star 2, B. And then the two index, which one is overlapping? Third index and fourth index, that is basically 5 and 6. That is j equal to 1 to 5th and k equal to 1 to 6. And the A tensor, that elements is A of ijkl, V is klmn. Then A star 2B is representation in this way. And then make it a particular case like matrix AB. So here we can write AIK, BKJ, and one summation is there. Here too, let us consider to come to the formal definition of Einstein product. So suppose A is a tensor of size 2n, I1 to In, again K1 to Kn. B is a tensor K1 to Kn and J1 to Jm. The Einstein product of A and B is denoted by star n. The operation, why star n? Because we need n number of element to overlap with the second tensor. That's why that A star n B is this way and that it is. So here the summation K1 to Kn means n number of summations are there. So like here, j equal to 1 to 5th and k equal to 1 to 6th, like this. So those people are interested to know about the tensors. So then they can talk about, they can go through this Einstein product, the foundation of a general theory of relativity. Okay. Now, this how another applications like solution of Poisson problem. So this is like, what do you call the higher dimensional PD. Suppose you have a d-dimensional Poisson equation. So that is with the Dirichlet boundary conditions. So del square u equal to f and u equal to 0 with the boundaries. The discrete d-dimensional Poisson equation can be written as Ax equal to b. So here you know that even if it two-dimensional, three-dimensional, all these things, we can make a matrix format Ax equal to b, where A equal to nd cross nd, like a nth to the power d and nth to the power t, and vector is like this. So in this way, when n is increased, n means number of interior points, d is dimension. So n and d, if it is increased, the traditional matrix vector based approach is impractical. Impractical in the sense that the number of computations time will increase. So how? Let's say consider a particular case. Suppose d equal to 3 and interior point, that is n equal to 100. Even if you do very high resolution problem, n is required 10 to the power 5 or 6. Whereas in the particular case, we are considering n equal to 10 to the power 2 or 100. That means interior grid points only 100 with Dirichlet boundary conditions. Then we can obtain the matrix 10 to the power 6 into 10 to the power 6 as per this nd cross nd. And the vector is this. So now you think about like only 3D problem and 100 interior points, it's required this matrix A is size this and vector is this. So if you increase the D and increase N, so this is kind of impractical to solve this problem. However, in Einstein product, we can write Ax equal to B, where A is a sixth order tensor. For a particular case, A equal to if 10 to the power 6 cross 10 to the power 6, and x equal to, we can write it in this way, and v equal to this way, then we can easily solve it. So this is one particular applications. So those are interested to know about this, they can go through this paper. Okay. Now come to the T product. So before the coming to the T product, let us consider, suppose A is a tensor of third order. So the third order tensor like PQN and n equal to 1 to n, AI is a matrix. Because the third order tensor we can cut in different slices. So here we consider the frontal slices. So the frontal slices is like V arc of A in this way. All are slices. And unfold of A is basically this. Now the operations, B arc, we can write that third order tensor to this matrix. Whereas the unfold of A is a third order tensor to this matrix. And V arc inverse is the inverse operation of B arc. And B arc inverse, we can write this. So here what happens, suppose A and B be two tensors, then the tensor product can be defined in this way. So either you can write B arc inverse, B arc of A, B arc of B, or fold of B arc of A into unfold of B, this way. So following this, we can write, suppose A is a third order tensor like A PQ3 and V is a tensor QM3. Then AV we can write in this way. Simple like a block matrix multiplication. People will say that what is the benefit? We are trying to make it the tensor and a block matrix and get it. No, it's not like this, just trying to make it a block matrix and do it. So this is the beautiful properties is because of the block circulant matrix. Because you know that a block circulant matrix can be diagonalized with the help of normalized DFT, discrete Fourier transform matrix. So that, let's say, Fn is a DFT matrix, discrete Fourier transform matrix, and 1 by square root of n, that is normalized. So this is Fn. And In is the identity matrix of size n. And this is the Kronecker product. And the B circ of A is like block circulant matrix. And F star n, that is transpose conjugate of this matrix Fn. Okay. So whereas, okay, and W is basically square root of unity. Exp, the exponential of negative 2 I pi n, I pi by n. Okay, now the algorithm. So this is the simplest algorithm I can say that. So no need to do it like a sarc of this, fold of, unfold of this. Use this simple FFT algorithm or FFT based algorithm for the computation of the product of two tensors. Suppose you have two tensors, A and B. A is size of this and B is size of this. Then what we'll do? The compute A bar or some different symbol, whatever that you can say. That is FFT of A in third direction. So this symbol is MATLAB notation of first Fourier transformation. And similarly, B is like this. Then the product is simple, C equal to A into B. Because once you make in a third direction, so it will give the block circulant matrix. And then multiplication is basically the product of two block circulant matrix. And after that, we can make it this inverse Fourier transformation. That means think about in your left hand side, two tensors are there. And the right hand side, you are transforming that tensors to a Fourier domain. That means use the FFT and get it the third directions, and that third direction is collections is block circulant matrices. And similarly, B also. Now, the left hand side, you are multiplying two tensors. That's not required. You can go to the right hand side or what you will do, multiplication of two blocks diagonal matrices. So this is easy and we can make it. So one example, let's say A is of size this and A fourth order tensor. So fourth order tensor is basically simple extension or recursive of third order tensor. So A into B. So this way, so A1, B1. So again, A1, B1 is a third order tensor. We cannot do it. We can make it in this and all are ready now. Then now A11 is a matrix. So simple multiplication, do it. So what we conclude here, the tensor product of A and B based on T product is reduces to matrix multiplication based on base size. Base size means, so here base size is 3 cross 3. Okay, so tensor product of A and V eventually reduced to a 3 cross 3 matrix multiplication. Okay, so how it is doing in this way? Let us come to the computations using Fourier domain. So suppose you have a fourth order tensor, fifth order tensor, nth order tensor. I already discussed in third order tensor. Now come to the fifth order tensor. So pth order tensor required p number of what you call first Fourier transform matrix or DFT matrix. NP, NP minus 1, N3. Kronecker product, all these things into IN means identity and B shark of A. Again, this B shark of A we can do recursively and finally reach a big matrix. And then we come to this. So multiplication of two tensors, basically multiplication of two block diagonal matrices. And whose blocks diagonal matrices with row blocks. How many blocks? Row blocks. And what is the size of row? Row is n3, n4 up to n3. So computation of tensors via Fourier domain is obtained by systematically recognize tensor to a matrix. The matrix computation result will be utilized for the tensor computations. Okay, so regarding this, the identity tensors, so it is difficult to go through this all. However, I'm just showing this is a transpose and then F diagonal tensors. So that means each frontal slice is diagonal. So because of the shortage of time, let's come to directly the applications. So let us consider you have a blur image. Last time, whatever that I gave examples like N1, N2, N3, suppose B, that is very blur, that we are not able to detect it. So now we have to get it a blur-free image. So our aim is to establish a blur-free image. So that image deblurring problem, we can write AX equal to B, where A is a blurring tensor that is need to be construct. And then that is not required also, not our aim. Our aim is also to compute X. First of all, we have to construct A. Without A, we cannot do. And then we have to compute X, that is X equal to A more Penrose inverse B or pseudo inverse of B. So this is blur image and this is reconstruction image. Those are interested, they can go through this paper and get it, read it. I'm open to collaborate, open to discuss, open to explain whatever things you need. Please write an email and say that we need to discuss this one. And one more applications like singular value decompositions. So you know that singular value decompositions is a decomposition and the special properties that all singular values are arranged in the decreasing order. And thus the least term of singular values are least effect. Suppose you have an image that is this, and then we can reconstruct, we can make it what you call visibility or like reconstruct this image to 5 singular value, 15 singular value and 25 singular and 10. So then people say that why we need that. Suppose you have a very high resolution pictures, not one, you have 100 high resolution features, images that you are getting where you visited last year or last month or yesterday. But your near or your loved one say that please share with me, but I don't have more space in my mobile. Okay, so what you'll do? So he said that okay, whatever that quality is okay, it should visible. I can see where you visited, what you did. Instead of quality, high quality, I need the importance of this picture, importance of the places where you visited. So then what you do, you compress that image and compress in such a way that your other party should see, should visible. So this is the way, mathematical point of view, I can say, or the tensor representation, say the 5 singular value, 10 single, 15 and 25. Even you say that, so this 25 singular value is okay, I can send it. And based on that, your near one, your loved one can get all this information. Okay. Again, like one more applications also, hidden secret color image or color video. Suppose you like to share your secret photos to other party, or like some near one, some your friends, some your colleague, but not with secretly. So this is a stenography, is a technique of hiding data within an ordinary files to avoid detection and then extracting it as at its destination. That means your near one can get it. So this is one applications. So here what we can say that input image. So this is the like what you call the flow chart for this. And some of these like color images and secret images, stego images, we can get it, and some videos. I'm not going to details of this. And thank you.
Thank you very much for your lecture. Dear colleagues, we have time to ask questions. Okay, let me ask a question just to specify. If tensor is a generalization of number, vector, matrix, and so on, what about numbers? Should they be real only, or could be also integer, Boolean, and so on?
Yeah, that can possible. There is no point.
It is possible.
Yes.
And the last ability is, for example, if it's how to say um, something like two names, nominal.
I don't get it. Nominal means?
Just names. For example, Evgeny, Alexei, Eduard, and so on, not numbers at all.
No, tensor is basically the name. It's like the representation, or like what you call the love, Love. So, what is the proper definition of love?
Yeah, but for
So there is
example, part of data can be not picture, not numbers, but names. Uh, is it possible
name.
to apply the approach?
No, I don't get it in that way. So tensor is like new name or new frame, I can say. So like a love. Love is a there is no specific way you can say that I can say this is the love.
Yeah, but specific, for example, everything that you show, it was, let me say, relative to real numbers, usual operations, and so on. But if you take Boolean numbers, variables,
Yeah, yeah.
0
Maybe
or
I
1.
lost internet connection or something. Okay. So I love chicken. I love flower. So there is no unique way.
Yeah, but we
Okay.
can generalize.
Is it audible properly? Yes.
Uh, Again, whether can we tensors approach generalize to this not usual numbers with not usual operations?
Uh, no, I cannot answer this way.
For example, we can use not usual operators, but for example, integer number we cannot divide each other because after division we can obtain not integer number, and we should let me say unify operators. But then again use tensor approach. It was a question. But I understand your answer. Thank you very much.
Mhm.
And, uh, other colleagues who would like to ask questions? You're welcome.
I have one question. First of all, thank you for your presentation. My question is, usually operations with tensors some algebra or mathematical transformation one matrix into another one. Can we apply some stochastic operations, some random operations?
Yes, we can do it.
Well, it's very interesting question because, for example, many population-based optimization algorithms can be presented as a big tensor. For example,
Yes,
matrix
hierarchy.
means
Hierarchy.
solutions and series of matrix means different generations. And
Mhm.
actually, algorithm, it's a transformation from one tensor to another one. So
Yeah,
it's a good idea to present a population-based approach like tensor operation using, for example, GPU.
yeah.
Do you know
So,
With specific
examples?
operations,
Sorry?
operators, with specific operators.
Yes, of course. And you need to apply a lot of specific stochastic operations, probabilistic
mhm.
operations.
So basically, I'm looking some statistical person who can collaborate with me. So like, the specific application oriented, I can give like mathematical representation, mathematical idea, so that we can start. But still now, that is the lack of applications in my domain, whatever that I published till now, around 40 to 50 paper. But statistical application still I am looking.
Yeah, and thanks to you, you are how to say, you launch our ideas about how can we use the approach to our own research. Thank you very much.
Yeah.
Yeah, thank you.
Thank you. I really appreciate. Yeah.
Okay, dear colleagues, now we have 11 minutes for the rest to take coffee or water, and then we will come back and we will have a regular session. And the first presenter will be Alexei Vakhnin. Thank you very much for your presence here. You can
Yeah. Thank you.
lead
Have
this.
a nice day. I'm going also for tea, coffee.
Okay.